Hello everyone, my name is Bernardo, and today we're going to be looking at some Lambda Calculus, and hopefully we'll learn a little bit about it, at least learn about what it is about, not necessarily like the whole theory behind it, because it's pretty heavy, but at least understanding, so when somebody mentions Lambda Calculus, you know at least what it is about, right? So to start, I'm going to show you some programming language logos. So this is the logo of Haskell, this is the logo of Clojure, and this is the logo of Racket. So have you noticed any similarities on those things? So I think the most striking one, at least when looking at the logos, is that they all have this Greek letter lambda in their logos for some reason. Like in the center of the logo, there's this Greek letter lambda. And also another side note is that all of these three programming languages are functional programming languages. And so yeah, and also on a completely different note, when you're programming on Ruby or Python, when you want to define an anonymous function, you use the keyword lambda. You probably heard like lambda functions, right? So what it is about lambda that is somewhat related to functional programming and to anonymous functions and to functions like in general, as it seems. So it all dates back to the 1930s when this folk here, Alonzo Church, created this thing called Lambda Calculus, which is a computational model. And a computational model you can think of, to simplify things, kind of like a framework, like an algorithm, a set of steps and a set of rules that you follow in order to compute a function, like a well-defined way to compute a function. Like compute a function like I have x squared and I want to, x is some value and I want to get the squared value of that. So how can I solve that? How can I compute that function? And later on the 1930s, the Alonzo Church, he published this paper on an unsolvable problem of elementary number theory, where he proved that the Encoding problem, sorry if my German is not perfect, which is a decision problem, was unsolvable. We'll not get into that problem particularly, but it's just funny because a few months later, Alan Turing, which a lot of people from computer science know, there's even a movie about Alan Turing, also published a paper where he created something called Turing machines, which is also a computational model, and proved that the Encoding problem was unsolvable. And Alan Turing got a little bit upset because Church published a proof of the problem he was working on earlier than him, and he didn't know about that. But he then went to the US and went to study under Church, with Church as his advisor. And during his period with Church, he published something that now called like Church-Turing thesis that basically stated that Turing machines and Lambda calculus were equivalent. By equivalent, we mean that you can define one in terms of the other, but also the set of functions they can compute are the same. The exact same functions that you can compute with Lambda calculus can compute with Turing machines. And it's funny because up until today, nobody has come with a different computational model that can compute a superset of that, like more functions than those things can compute. So normally when we say that a function is computable or not, until today, somebody discovers something different, it's not proven that this is the only set of computable functions. So when we say something's computable, we normally say that we can represent that computation in Turing machines or Lambda calculus. And when we say that the language is Turing complete, we normally say that that particular programming language can also be used to compute all the computable functions as defined by the set of functions that Lambda calculus and Turing machines can compute. So I'm going to stop a little bit with the history and theory here, and I'm going to try to do this in a completely different way. So what I'm going to propose is that we're going to take on a programming challenge using whatever mainstream language that you want. I'm going to be using JavaScript for a few reasons. First one is that, it's one of the most popular languages, and also because I can just come here and open a JavaScript console in my browser, and everyone can have a JavaScript environment ready to go. So that's one of the reasons I'm going with JavaScript. But a lot of these ideas you can use in Ruby, Python, if you want to play around with the ideas of Lambda calculus. Okay, so the subset of JavaScript we're going to program is that we can write JavaScript that is one of those terms. And a term can be either the name of the variable. You can type the name of the variable. You can define anonymous functions with exactly one argument. In JavaScript, we do that by the arrow syntax, the fat arrow. So x, fat arrow, and then body, where the body is also a valid term. You may also use parentheses to say where the body of the function ends. And also another thing you can do, you can apply functions to another, you can have two terms like A and B, and then you apply function A to input B. And another thing is that we're not allowed to use any externally defined variables or functions like the standard library. You're not going to use numbers from the language. You're not going to use Booleans. You're only going to use functions that you define, and then you can apply those functions. And you can only refer to a function if you receive that function as the argument of your function. Okay. So just to show some kind of things that you can type in this subset of JavaScript, you have like the simplest one, which just receives something and then returns it without doing anything with that. You can also like apply that the same thing. You don't need to be like inside a function. You can define two functions and apply one to the other directly. And you can have like more complex things since all functions have exactly one argument. If you want to receive like two things, you can do a function that returns another function that then apply the first argument to the second one 4 times in that case. Okay. If you want to play around at home with any other language, it'll look like something like that in Python or in Ruby. And by showing this, I think I can kind of make you understand why I went with JavaScript, because it don't have all this Lambda noise going on, so it's a little bit clearer. Okay, so the funny thing about programming JavaScript that way is that it is Turing complete. So what I mean, it can compute all the functions defined by the all the I told before. So just to make you maybe believe me, I'm going to show you a factorial function implemented that way. So this is the factorial function. I know it doesn't make much sense, but we're gonna get to that at least at some point. So I'm just gonna cons factorial, and I'm going to define that. But the thing is that we cannot just pass JavaScript numbers, because as I said, we don't have numbers. You see, I'm not doing any multiplication or whatever. I'm just like calling functions and applying functions, because numbers and Booleans and all the values will also be encoded as functions. We're going to use functions to encode those things. So just imagine for a second that we have this function from number to number that kind of do the conversion between the normal JavaScript word and this function only JavaScript word. And in fact, I have them here, so I'm just going to copy from my notepad here and paste here. We're gonna take a look at those things, at least the zero and successor function. But now I can technically copy this code here, paste it into my JavaScript thing, and then I have the factorial of 5 is 120. I know it's kind of like, what is even happening, right? Oh, sorry, I did a typo. So factorial of 6 is 720, and yeah, factorial of 4 is 24. So like, you're probably like, what is even going on? When I look at that, it doesn't make any sense. So let's try to get to that. But before, let's do a step back and talk about Lambda Calculus. After all, this talks about Lambda Calculus. So just to give you a little bit about Lambda Calculus, to put it in a really, really simple way, you can think of Lambda Calculus as this really, really small programming language. And it's a really, really small programming language that basically everything that this programming language have are anonymous curried functions. By anonymous, I mean that function doesn't have a name. So I can only call a function if I receive that as an argument of the function I'm defined. I cannot like call it by the name. I have to receive it somehow. So I cannot like name a function and call it by that name. And also curried mean that they have exactly one argument. So again, if I want a function with 2 arguments, I should create a function that returns another function, right? And also, as a programming language, has a syntax. I'm simplifying some things here because depending on where you look, you're going to see some different syntax. But in general, the syntax consists of 3 things. So you have variables. So variables are named, normally just 1 letter, but I'm going to use multiple letter variables just to make it clear. And also, you have abstractions. So you can think of abstractions as function definition. It's basically the same thing. And the idea that you abstract the value x, so you don't know where x comes from. So it's an abstract value that we receive. So, but use the lambda symbol here to define this abstraction, to define this function, and then you use a dot, and then everything to the right of the dot is the body of that abstraction. It's like it's everything to the right. So if you want to end and define where the abstraction ends, you can wrap that in parentheses. And also you have application. And application in this Lambda Calculus syntax is just opposing those two terms, and then you apply the input A, the function A to input B. And also, since they're just like next to each other, there's an order of application, and the application here is left associative, which means when I have like ABC, it means that I want to apply function A to input B first, and that's going to be return another function which I'm going to apply to input C. If I want to change the order of application, I can use parentheses to say, hey, first apply B to C, and then apply function A to the result of that. So okay, so remember this thing that I showed on JavaScript. This is kind of like mimicking some kind of Lambda Calculus, and in Lambda Calculus, those things would look something like that. So it's pretty similar, you see. Again, we have the simple function that returns whatever it receives, and have like more complex one that receives 2 things and apply the first one to the second one 4 times. Okay, so now we know a little bit of the building blocks, and let's try to get as close as we can to building the factorial function from scratch. So if you try to implement like a recursive factorial function in JavaScript, this is probably what you like implement. So you have like the base case that checks on n equals 0, return 1. Otherwise, you return n times factorial of n minus 1. And so what we need to construct all these things that we are using here in this Lambda word. So we need a way to represent numbers like 0, 1, and the n we receive. So we need a way to encode numbers, as I said on the factorial example. We need a way to encode booleans, right? Because the quality here is going to return a boolean. We need a way to check if a number is 0 and return a boolean. We need a way to multiply numbers. We need a way to get like the predecessor of the number. We don't need we just need to get n minus 1 given an n. And we also need a way to do recursion, which seems simple, but in fact it's not because our functions are anonymous. And we need a way to do branching, like I have a boolean and I want to choose this path or this path depending on the value of the boolean. So this is kind of like the to-do list we have to go through. And just to, I'm gonna try to go through all of them, but not all. So let's start with the booleans. So, okay, let's try to encode booleans. So this is, I think, is a good point where you need to slow down a little bit and think, what is about encoding booleans? So when I say encoding booleans, I want to use functions to represent values true and false. So I want to have like, depending on the way I use the functions, this should be representing true or false. There are infinite ways of doing that. And I think a good way of thinking of a useful encoding is to think, what do I use that thing for? What booleans are used for? So when I think about booleans, the main use for booleans is to do branching, right? I want to, depending on the value of my boolean, I want to pick either path A or path B. Of course, I want to do some operations on those booleans as well, like and, or, and combine those booleans. But in general, I use booleans to do, do branching. So, okay, we know that the boolean will be encoded as a function because everything is a function. This is the theme of the thing here. Everything is a function. So one good idea of doing is like, okay, if I want my boolean to pick between two things, why don't I make my boolean be a function that receives those two things and then picks whatever it wants depending on whether it's representing true or false. So I can make my boolean receive the then and the else path kind of, and then if it is true, it's gonna pick the then path, and if it's false, it's gonna pick the else path. Just to give you an idea of why this whole thing kind of works. Well, first of all, this is also called as Church booleans or Church encoding for booleans, basically because Church used this encoding for booleans in some of his papers. And in our JavaScript world, it would be something like that. And I'm gonna, of course, copy that and paste here, just to give you kind of like an insight of why this is actually representing true. I'm gonna do a trick here. So I'm going out of the function word, and I'm going to call that function with two things, true, the JavaScript true and the JavaScript false. And when I do that, it returns true. And if I change the function true to the function false, you see that it picks the right value depending on whether it's true or false. I'm just using true and false without the last letter just to not conflict with the JavaScript ones. Okay, so this seems that it is encoding true and false because I can just change the function and I get like a different result, but I need to do some operations. So I'm gonna try to just do one operation and then make you believe that all the other are possible. So let's try to do a simple one, the not function. So the not function is a really simple function that receives a boolean A and then it flips. So if it receives a true, it should return false. If it receives a false, it should return true. And you see how I just explained the function is kind of like the answer to that question. So if A is true, then the result is false. Otherwise, it is true. So if I would like implement my own not function in JavaScript without this Lambda word kind of related, I could probably implement it something like that, right? So I forgot the arrow here, but anyway. So my not would receive an A, and then if A is true, it's going to return false. Otherwise, it's going to return true. But in our Lambda word, we don't have these operators here. We don't have if then else. However, we encoded our booleans in a way that the booleans themselves do kind of an if then else. If I pass two things to that boolean, it will pick the first or the second one depending on what is encoded. So I can implement my not function by having this function that receives the boolean A. And then since A is a boolean, I can just pass false and true to that. And A is gonna pick false if A is true because true does that, picks the first one. And we're gonna pick true if A is false because false does that, picks the second one. That's how we designed the encoding. So in our JS word, it would look something like that. So see, I just apply, I get a Boolean, and then apply false and true here. And if I copy that here, I can try that out, and I can see that true returns the function false, and false returns the function true. We know that the function false here because JavaScript. I mean, I told you it's anonymous function, but JavaScript doesn't let us do that. It always gives that name when you define it as a constant. But anyway, so you saw that it returned the actual value. So it seems to be working. And for the other functions, you could do the same logic, because if you have branching, you can basically use the branching to build the whole truth table. So just to give some examples in the JavaScript word, would be something like that. And I'm not so on a word it will be something like that. So you can just keep doing branching and choosing the right transformations. So I'm just going to show the end. So end true should return true, and end when I put false in anywhere, it returns false. Yeah. So all values are false unless both of the inputs are true. So just to give you an idea that yes, we can do all possible Boolean logic functions here. And if you have and not, you technically can do everything, right? NAND logic. Okay, so now we have encoding for Booleans. I hope that I convinced you that you can encode Booleans using only functions. So let's try to encode natural numbers. So this is going to be a little bit trickier because natural numbers are actually infinite possible natural numbers out there. So we want to encode like 0, 1, 2, 3, and so on and so forth. Again, there are infinite ways that you can do to encode natural numbers. And again, I'm going to ask the same question. What do you use natural numbers for, right? So natural numbers are normally used for counting things, right? So I have $0 in my pocket, and I have 3 bills due tomorrow. I have n things. So we use to counting. So one thing, again, I'm just going to show you how Church did it. So also known as Church numbers or Church encoding for natural numbers, is that it encodes the number as the number of times the first function that receives is applied to the second thing it receives. So put it another way, a natural number n is encoded as a function that receives 2 things, and apply the first one to the second one n times, right? So just to give you some examples, 0 would be encoded as receiving 2 things and just returning the second one. And then 1 would receive 2 things and then apply the first one to the second one exactly 1 time. And then 4 would do that 4 times. And just to, but we need to know that we can encode all possible natural numbers, right? So, but natural numbers have this, has this transitive property where if we have 0 and we have a function that returns, n plus 1, then we know for sure that we can have all possible natural numbers in the set of natural numbers. And so, okay, 0, we already defined how that was, right? So 0 was this thing here. And so 0 would be something like that. In JavaScript, I'm not going to copy because I had copied to show you the Factorial demo. And so let's try to think about the successor function. So successor function, we know it receives the function encoded number n. And we need to return the function encoded, the Church encoded number n plus 1. So we know that since we're going to return a Church encoded number, we know that it's going to have this shape. So it's going to be a function that receives 2 things and then returns f applied to x n plus 1 times. So we don't know how much n is, but we can. So we need, if you start with applying f to x n times, we can then just apply 1 more time, and then in the end we're going to be applied f to x n plus 1 times. So the trick here is that we start by just calling the n we received with f and x. So this thing here would return the result of applying f to x m times. But since we want to do the value n plus 1, we need to apply f 1 more time. So we need to do that. So this is the successor function. It's actually pretty simple in this Church encoded thing. So again, in JavaScript, it looks something like that, not that complicated. Of course, it sometimes takes a while to scratch our head around that. I won't copy it because I had copied that before, but I'm just going to use some examples here. So I'm just going to copy those things here. And then use the 2 number that I had defined before that converts back to JavaScript. So you see that 2 number 1 is 1, and 2 number 3 is 3, and 2 number 100, which is supposed to be 99 plus 1, is 100. So yeah, somehow it seems that it is working. Successor is encoding the next one. Okay, So I hope that now you at least believe that it's possible to encode natural numbers using only functions. I think that's the main barrier. Is like, okay, now I believe that we can do that. So now if we want to implement factorial functions, we need all of those things. We need function stack number, multiplication, predecessor, and those things are like, they would be nice to scratch our heads around, but it's only a 30-minute talk. So I'm just gonna unfortunately just show them, and then so we can use them to build our own factorial function in the end. So these are the definitions. The predecessor function, I think, even if I try to explain, I would fail miserably because it's, I don't know, I'm not even sure that I understand the predecessor function completely, and I scratch my head around that a lot of times. So in JavaScript, it would be something like that. I'm just gonna copy that just to make sure it's kind of working, and we have that for our factorial function. So we 0, 0, yeah, 0, see return true, so 0 is 0, and 1 is not 0. Let's try just the multiplication. So multiplication, we need to multiply, I don't know, from number 5, and the second argument will be from number 4. We need to also convert that back to JavaScript numbers, to number. And yeah, times 5 times 4 is 20, 5 times 6 is 30. And you can also try the predecessor function. So let's crawl predecessor here. So before 5 is 4. So just to give you like hope that, you know, we can actually implement those functions in this way. Okay. The reason why I skipped those things because I want to talk about if then else and recursion, because I think when I was playing around with those things in Elixir, in JavaScript, in Encoding evaluated language, I took a long time to me to realize a few things. So let's talk about if then else. So we saw the Booleans, and you might be thinking, isn't like if then else just applying Booleans to the branches? I mean, well, yes, it depends, because JavaScript is eagerly evaluated. So the problem with that is that when I'm trying to do, like, I have my true here, and when I'm just picking two constant values, it is okay, because constant values, we know that, you know, don't need to, never gonna halt. For example, imagine we have like a recursion that would halt forever in our factorial case. So the thing is, JavaScript is eagerly evaluated, which means it evaluates the arguments of a function before applying the function to that. So if I do like a console log just to simulate some kind of side effect, you see that in a true if, we would only log the first one, right? But since, oh, sorry, this was supposed to be that. So we'll only evaluate that. But since JavaScript is eagerly evaluated, what happens here is that it evaluates both arguments before actually evaluating the result of that. And this is okay if I'm just returning like, you know, regular values. But in the case of our factorial function, we need to do recursion. In our like else path, we call ourselves, we do like recursion. And if we use that to implement our if for our factorial function, would always evaluate the recursive call, and therefore our function would never return. So we need to do a trick here. And the trick here is to defer the evaluation. And a way to defer the evaluation in JavaScript is that we can wrap those things into functions, and those functions will only be called when I call them with something. So you see, no console log was done, and then I can call it with anything, and then only the chosen path would be evaluated. So in our Lambda world, this will look something like that. So I have my if function receives the Boolean b, and then receives, of course, the then and the else path. But the then and the else path is not the value that we want. It's a function that evaluates to those values, and evaluates and ignores the input. And then we can, you know, call the Boolean with those things to choose the path. And then only after we chose the path, we evaluate that by passing some argument. So in our JavaScript world, it looks something like that. So I'm just gonna copy that and just do, so I can try to, instead of doing that thing myself, I can just see if it works. So I don't, if then else and true, you see it's gonna only evaluate the y. And then if I do false here, it's going to evaluate. So I have to trick the JavaScript environment. And if you're doing that in Python, in Ruby, this will be true as well, because those are eagerly evaluated languages. So yeah, so I think it's a good side note if you want to try this at home. So okay, now we have the if then else that works in our JavaScript Lambda word, and now we need to do recursion. And the recursion is tricky, because the problem with recursion in Lambda calculus is that, I mean, all functions are anonymous, right? And since all functions are anonymous, we cannot call ourselves, because I cannot refer, I'm defining the body of the function. I cannot call this function that I'm defined by its name, because it doesn't have a name. So I need to receive it somehow, right? So the solution here is to abstract yourself. So what I mean by that is that when you're defining your recursive function, so imagine have this function that receives x, do something with that, and then call itself again. How can I call itself since it doesn't have a name? So the solution when I'm talking about abstract yourself is creating an abstraction that is created by receiving the concrete version of the function, and we're going to see what that's about, and then returns the actual function, and now myself have a name, and I can call it and do recursion with that. So just to give you what it would look like for a factorial function, we just define our factorial functions as a function that receives the factorial, right? So in order to build a factorial function, I need to pass the build factorial to that. And here's the other problem that we're going to see. So in JavaScript, it looks something like that. And the problem with that, I don't know if you noticed, but the factorial function is only this part here, right? It's only from the end. And so in order to build the factorial function, I need to call abstract factorial passing the factorial itself. But in order to build a factorial, I need to do, so it's kind of like a circular dependency problem, right? Just to kind of show you, like, because in our case, we only call factorial in the recursive case. So we could technically use that factorial, and I'm just gonna pass nothing here just to make it, just fake the function. And then I'm gonna pass like from number here, and I'm gonna do 0. So, okay, so to number, and that will work because this function that was supposed to be here, that's definitely not a function, this 0 here, this whatever, this undefined, this will never be called, so there's no problem with that. But once I need to do one recursion, when I'm trying to call that function, it is not a function, right? Because I just fake it. I could technically, you know, I could keep like calling abstract factorial here, right? And fake it one more time. And then, but then it works for 1, and then for 2, it doesn't work because again, it's going to recurse, and then it's going to call this factorial, okay, and then recurse again, I'm going to call this undefined factorial thing. So if you think about, I need a way to kind of like, you know, repeat this thing here. I need to call abstract factorial of abstract factorial of abstract factorial of abstract factorial, and then, okay, this would work with 3, but then would not work with 4. So in some way, I need to kind of like infinitely do that, you know? I need to keep doing that somehow. And now it works with, I don't know, maybe 7. So yeah, so the problem here is that I need to kind of like repeatedly call abstract factorial with itself. And that's where fixed point combinators come into place. I'm not going that deep into fixed point combinator, but I think it's a good thing to mention here. So fixed point combinators are this special combinator slash function that has this property. So when I apply that function to some input f, it is the same as applying f to that same thing. So if you keep expanding that fix of f, you're going to have like f of fix of f. And then if you keep expanding, you're going to have this thing here that infinitely calls itself like f of f of f. And if you think about it, if I change this f for my abstract factorial, it's exactly what I want. And you might think that this is kind of like, oh, this is impossible. But in fact, there are infinite combinators that have this property. If you search around, and again, I'm going to mention that, but because I lost a lot of time realizing that, is the Y-Combinator. You probably heard about that. But the Y-Combinator has that property, is a fixed point combinator. But the problem is you cannot just go ahead and do that in JavaScript. So if you're trying to, or Ruby or Python or whatever, because it will keep applying abstract factorial because it works only on a lazy evaluated environment. So in JavaScript will keep like applying abstract factorial to itself over and over and over again and would never return. So we cannot use that in JavaScript because it's eagerly evaluated. But fortunately, there's another combinator. One example of them is the Z-Combinator that works in eagerly evaluated environments. So the trick is kind of similar to what we've done with the if then else thing. That's the reason why I talked about it. It kind of like defers the evaluation of the recursive call to just be called when we actually need it. So you don't keep like creating these infinite calls. And the definition is like that. I'm just going to show you that it works in JavaScript. So in JavaScript, it would be something like that, right? So I'm just going to copy that thing here, and then I'm going to define my factorial as Z applied to abstract factorial. And this will be similar to the ABS factorial, and so on and so forth, because that's what the fixed point combinator does. So now I can just go and try to call, and Zoom is getting on the way. I can just call that here. So factorial of 5 now works, factorial of like 7, factorial of 8. Maybe it's going to take a while, but yeah. So it is working out because what the Z-Combinator is doing is kind of like whenever you need the next recursion, it applies factorial again and again and again. So yeah, so that was the road. Sorry for being maybe a little bit too fast, but I think the key takeaways here is that Lambda calculus is about functions and functions all the way down. So everything is functions. And in fact, you can model numbers, you can model Booleans. Like this is a key takeaway. You can represent numbers and Booleans and whatever using only functions. And in fact, this is too incomplete. You can compute anything, I mean, anything with an asterisk, anything that we know up until today that is considered computable. And also, I think it's a good thing if you want to go ahead and learn more, especially the theory behind it, because it's also the theory behind functional programming languages such as Haskell. Maybe that's the reason why Haskell has a lambda in the logos. So yeah, thank you everyone. I have this repository here where I have some examples in JavaScript, some in Elixir from previous talks. So if you want to check that out, if you don't copy that, you can ask me later and I send to you. Thank you.
Wow. That was really fast, Bernardo.
Yeah, sorry about that.
Awesome. No. A lot of interesting stuff. Really. I'm also remind you that if you have any questions, I'm checking here in the mobile application. So if you have any questions, please let us know in order that we can ask those questions to Bernardo. But now that you were giving the talk, I want to ask you something, Bernardo. Why do you think that it's important to learn about Lambda Calculus? Why do you think it's important right now? No, because it's a long time ago, not that Church proposed this, and also we have the Turing machines, also the other model. But why do you think it's important right now to know more about Lambda Calculus?
Okay, that's a good question. Thank you. I think the first one for me personally is because I think it's fun, and I think for me it's kind of like it was mind blowing when playing with that. Like, what is even happening? And I thought it was kind of fun and made me, I think, shift my way of percepting like what computation is and how it works, right? And I think for me that's the number one reason. But also it's funny because through all these years we've been building machines based on top of the idea of like Turing machines that you have like mutable state, and then you change state, and then we did that like for all long because that's the way we could implement actual machines. But then over time we started creating higher and higher level of abstraction languages. But then, and the thing is, we went all this way through, and then now when you think about like higher level languages like Haskell and those things, actually they are heavily based on the idea of Lambda Calculus. They basically implement like a kind of like a Lambda Calculus evaluation engine on top of a Turing machine, right? Because it's possible because they are equivalent, right? So I think it's a lot related to like functional programming languages. It helped me understand some concepts of functional programming language. For example, if you think about the Church numeral, it is actually just a reduce. Like if you think about like the function reduce, it just like reducing over if you think about just like applying the same function over and over again. You can think of that as a reducing over like a void, a list of voids or whatever. So I think helps understanding and thinking about functional programming language. I think that's the other reason.
Okay. I'm checking if we have any other question, and okay, I'm checking right now if we have more questions, but related to the demo that you show us about how to implement and use Lambda Calculus using languages like JavaScript or Ruby. Do you think that those languages can do more about how to use Lambda Calculus, that the theory behind Lambda Calculus, in order to maybe improve the programs that we do every day? Do you think that that would be important to that?
Okay, I don't know if I understand the question. I mean, like the people implementing those mainstream languages, if they could use like the theory behind Lambda Calculus to implement the language itself. I'm not sure if I got the question right. That was the question.
That's one part of the question, and the other is that if you have those tools for, in the language, that you can also improve. Not that you have better tools in order to create better programs. No, using those those languages.
Yeah. I'm gonna speak a little bit about previous experience because one of the jobs that I had like in the previous year was working on a company that was developing its own programming language, and the programming language was based on normal proofs and stuff like that. But the runtime of that language in the end was just Lambda Calculus. Actually, there was other things going on, but basically, when you look like the abstract syntax tree after you remove the types, it was like Lambda Calculus. Like you have variables, you have application, and you have abstractions. But the funny thing is that there's a lot of research on top of that because I just talked about like untyped Lambda Calculus, and there's like a lot of things going on top of like Lambda Calculus, like typed Lambda Calculus and other like. To be honest, I'm not an expert on that, but a lot of people develop a lot of things related to type checking and what has happened. Okay, I think my screen share stopped. And I think so. Yeah, I think there's a lot of people developing like formal proof languages and things related to that, which in the end are going to increase like safety and correctness of the programs. And a lot of those things are built upon Lambda Calculus. And the programming language that I was working on, the implementation was actually built in JavaScript, which is funny. People are, why do you develop like a proof language in JavaScript? But it doesn't matter because we just like implemented the interpreter in that. But on top of that was JavaScript at the bottom, and Lambda Calculus, and then on top of that, there was a lot of like type system shenanigans that was happening there. But I think it's a good basis because there's a lot of research on that. But to be honest, I'm not a complete expert on that. I was mostly doing JavaScript stuff over there. But yeah, that's where I learned a little bit about Lambda Calculus and got me interested in that.